Welcome to the 18th lecture on electrodynamics. Today's topic is energy of a continuous charge distribution or electrical energy stored in a volume of a charged body. 18th lecture electrodynamics for BSc students, MSc and NET students can also study this. Energy of a continuous charge distribution. Here the equation we get is W is half epsilon 0 all I mean E square d2. The energy of a charged body is given by W is half epsilon 0 all I mean E square d2. And look here, if V is the potential finally established in a volume of a continuous charge distribution, the energy stored in it is given by W is equal to V by 2 into Q. You know work done is a VQ, but when potential gradually increases from 0 to V, we have to take average value. Average value is V by 2 for potential. So work done is V by 2 into Q. നമ്മൾ പൊട്ടൻഷ്യൽ വർക്ക് കണ്ടുപിടിക്കുന്നത് വി ഇൻറ്റു ക്യൂ എന്നാണ്. അത് എവിടെയെങ്കിലും പൊട്ടൻഷ്യൽ വി ഉണ്ടെങ്കിൽ ചാർജ് ക്യൂ ട്രാൻസ്പോർട്ട് ചെയ്യാൻ വേണ്ട വർക്കാണ് വി ക്യൂ. പക്ഷേ പൊട്ടൻഷ്യൽ ഒരു കപ്പാസിറ്ററിലേത് പോലെ 0 to വിയിലേക്ക് ഇൻക്രീസ് ചെയ്താൽ അവിടെ എടുക്കേണ്ടത് ആവറേജ് പൊട്ടൻഷ്യലാണ്. ആവറേജ് പൊട്ടൻഷ്യൽ വി ബൈ 2 ആണ്. വർക്ക് ഡൺ വി ബൈ 2 into ക്യൂ. Therefore we can write W is equal to half V integral V rho d2 because look here, rho is the volume charge density, so rho d2 integral rho d2 is Q. So in the place of Q we put volume integral rho d2 in the place of potential we write V by 2. Half is taken outside. So W is half volume integral V rho d2. Remember Q is integral over tau rho d2. That is equation number 1, which is very important. Now we remember the differential form of Gauss law. That is del dot T is equal to rho by epsilon 0. That we cross multiply, we get rho is epsilon 0 del dot epsilon 0 into del dot equation number 2. In the place of rho, in equation 1, we put rho, that is W is equal to half volume integral V epsilon 0 del dot E. In that manner, we can write d2. That we write in order. Epsilon 0 we take out of the integral sign. W is equal to epsilon 0 by 2 integral V del dot d2. That is question number 3. And there is a vector identity in the form that you have to study by heart. There is a vector identity in vector calculus in the form V into del dot T is equal to del dot VE minus E into del dot V, equation number 4. This is a vector identity. V into del dot T is equal to del dot VE minus E into del dot V, equation number 4. That we put in equation number 3. This equation number 4 we put in equation number 3. Then we get W is equal to epsilon 0 by 2 all integral del dot V minus E into del dot V d2. And you look here, V is a scalar function, so del dot V has no particular vector meaning. Del dot V is equal to del V. V is a scalar function. So need not write dot there. The reason is written on the margin. The margin. The del of V is a scalar function. So del dot V is equal to grade V. No need of putting dot. Therefore, we write W is equal to epsilon 0 by 2 volume integral del dot V minus E dot del V d2. We can put in that manner. Del V is a vector, E is a vector. So if there is no dot in between E and del V, it has no meaning. That is why we put dot in between E and del dot V. Del V. Del V is vector, E is vector. So that is a dot product. So that we write again W is equal to epsilon 0 by 2 volume integral. We remove the bracket. Del dot V d2 minus epsilon 0 by 2 volume integral E dot del V d2. And now the first integral we make to 0 value. The first integral in the RHS, we show that it is very negligible. You look here. The first volume integral in the RHS can be converted into surface integral using Gauss divergence theorem. That we have studied, we have seen a number of times Gauss divergence theorem in vector calculus. That is volume integral del dot V d2 is equal to surface integral V d2. You remember the theorem? We have studied volume integral del dot dV is equal to surface integral E dot ds. Here V is coming as a constant term. I shall say once again the Gauss theorem. Gauss theorem is surface integral, volume integral del dot E dV is equal to surface integral E dot ds. In the place of you take VE. V is a constant term, not a vector. Therefore, the Gauss theorem with VE can be written as volume integral del dot V d2 is equal to surface integral V d2. That we put in the above equation. In the equation, we put this value in the above equation. In the place of del dot V, we put this value. Now we get W is equal to epsilon 0 by 2 volume integral del VE dot ds minus epsilon 0 by 2 volume integral E dot del V d2. And you look at the first term. In that term, there is V, E and ds. Epsilon 0 by 2 is a constant. There are, in the first term in the RHS, there is V, E and ds. And you know, V usually proportional to 1 by R. Potential relation we know, V is 1 by 4 pi epsilon 0 q by R. It is written in the side margin. Here electric field is proportional to 1 by R square because E is equal to 1 by 4 pi epsilon 0 q by R square. And ds area, it is pi R square in that manner. It is proportional R square. So these proportionality values we put in the first term of the above equation RHS. That is VE ds proportional to 1 by R square into R square. R square is the proportionality term for ds. Then we have an argument here. You look here. On cancellation, we can say integral V ds proportional to 1 by R because R square and R square cancels. Therefore, if R is large, the first term, the RHS of the above equation, the term surface integral V dot ds is negligibly, vanishingly small. R വളരെ കൂടുതലാണെങ്കിൽ മുകളിലത്തെ ഇക്വേഷനിലെ ആ ഫസ്റ്റ് ടേം അത് വളരെ ചെറുതാവും. അപ്പോൾ അവിടെ നമുക്ക് 0 കൊടുക്കാം. So W is equal to 0 minus epsilon 0 by 2 volume integral E dot del V d2. And we have studied E is minus del V. Electrical field is a negative gradient potential. We have studied in the beginning of this chapter. So here in the place of del V we can write minus C. So W is equal to minus epsilon 0 by 2 volume integral E dot minus C d2. That is E is equal to minus into minus plus epsilon 0 by 2 volume integral E dot E d2. E dot E is E square. W is half epsilon 0 volume integral E square d2. That is the final answer. The energy stored in a charged body, volume element, volume is given by this equation. Hence, the electrostatic energy is stored in a volume charge distribution. Then energy is stored per unit volume. Energy per unit volume. For that, we have to divide it by volume. That is U is equal to energy density. Energy stored per unit volume is called energy density, equal to W by volume, half epsilon 0 volume integral E square d2 by volume. Volume term cancels. Volume integral d2, that term cancels. We get U is equal to 1 by 2 epsilon 0 E square, equation number 6. This is the energy density, energy per unit volume of a body, charged body. And this equation is familiar. This equation you have studied in your plus 2 class, energy density in a capacitor. When we study energy W is half CV square, then the step coming is energy density. And that relation here we have determined using vector identity in vector calculus. That is given, that is a part of our syllabus. So U is equal to half epsilon 0 E square is the energy per unit volume or energy density. And the question may be like this. Show that the energy density over a charge distribution is half epsilon 0 volume integral E square d2. That is for a complete volume. And for unit volume, show that the energy density over a continuous charge distribution is half epsilon 0 E square. The matter is very easy. You remember, we start with an energy equation, W equation. We start with a W equation, that is W is half volume integral B rho d2. And finally we reach an equation with the E. Both are work equation, energy equation. We start with a W equation here and this W equation contains V. And finally we reach an equation of W in terms of V. Both are same. Both equations are same. And this is an equation in terms of the field E. That is all. And with this, our first unit of electrodynamics is over. In the next class, in the next lecture, we start with the second unit. That is all. Thank you.